Dear students, today we will start unsupervised machine learning algorithm, which is called K-means clustering. Up till now, we have covered different algorithms that fall under the category of supervised machine learning. But today, I'm really excited that we will start unsupervised machine learning as well. And I will explain what I mean by unsupervised learning. But like before, I would like to give you reference books for this material. So I have referred these three chapters for this module. So chapter 9 from Bishop's book and chapter 14 from Max Bramer book. This is not machine learning book but a data mining book. And chapter 8, again, data mining book from Kumar. For you, I would recommend that if you want to see introductory material or very basic material on K-means clustering or clustering in general, to follow chapter 14 of Max Bremer's book. So before diving into unsupervised machine learning or K-means clustering algorithm, I just want to refresh your memories about taxonomy of machine learning. This is we have already seen in first module, but this is just to refresh your memory. So machine learning has different kinds of algorithm, or machine learning is divided into different subtypes of algorithm. Up till now, we have covered supervised machine learning. And in supervised, we have done classification and regression. Regression was actually the last module which we covered. In supervised machine learning, important thing is that we have labeled data. So you are given data set in this form like xi, x sub I with y sub I. So this is like feature vector with corresponding label or the correct output. So we already know correct output for a given feature vector. This is supervised machine learning, right? In unsupervised machine learning, we have unlabeled data set. We don't have labels. We have only xi's. So we have only x1, let's say x2 till xm. This is the complete data set we have. Now we don't have labels. We don't know the correct answer for the given data set. We just know feature vectors. We are just given feature vector. So that is called unlabeled data, and unsupervised machine learning deals with unlabeled data. In unsupervised machine learning, basically we'll do clustering. Clustering has different types. So K-means clustering is one type of clustering algorithm. So clustering is one subtype of unsupervised machine learning. Dimensionality reduction. If you remember, we already discussed PCA, principal component analysis, when we were doing module on feature selection or feature reduction. So that comes under the heading of dimensionality reduction or unsupervised learning. So these are two basic subtypes of machine learning: supervised machine learning, unsupervised learning. And the third major component of machine learning is reinforcement learning. Reinforcement learning is not part of this course, but just for the sake of completeness, reinforcement learning is a bit different from supervised learning and unsupervised learning, and it deals with punishment and reward mechanism. So let's say you have a robot or an agent that is interacting with the environment, or in case of robot is interacting with the real scenarios, and based on the actions, whether robot will have a reward if the action is correct, and if robot takes wrong action, then robot will have a punishment mechanism, or punishment penalty would be given to a robot. So that is how that in reinforcement learning, robot or agent learns from the environment based on reward and punishment mechanism. So these three are basic types of machine learning: supervised machine learning, that we have covered up till now. Unsupervised machine learning will start or will begin today, and reinforcement learning is not part of our this course. So this is we have already seen. This is typical setting of supervised machine learning. So you are given set of possible instances x. So this is possible instances x, and we are trying to find a function that maps inputs to outputs. So x are feature vector on input, y is our output. And We are trying to find the best hypothesis from superclass of capital H of possible hypothesis. In supervised machine learning, out of those H, we'll find best small h that best approximates this function that maps inputs to output. But the important thing is training example has xi and yi. Yi is correct label or correct answer for a given data for a given feature vector. For example, X is an email and Y is label whether this email is either spam or not spam. Or in terms of image, let's say you give an image of certain object and Y would be correct label for that object. So if this is an image of a known personality or celebrity, then label would be name of that person. Right? So this is supervised machine learning. And in output would be hypothesis that best approximates this function f that maps inputs to outputs. That is supervised machine learning. So supervised machine learning is about function approximation in other terms, right? Unsupervised learning is about description as opposed to approximation. And I will explain what I mean by description. So let's say if you are given this kind of data set and there are no labels, this is the total data set we are given. Unsupervised machine learning will try to find patterns among the data, and based on the patterns or structure, it will divide data set. It will make clusters. So let's say this is unsupervised machine learning algorithm, and based on certain features, different categories of images are subdivided. So let's say if images have very specific shape of face, and if they have pointed ears, they are called cluster. So this is clustering algorithm. So let's say this is cluster one. If shape includes some kind of feathers, this is cluster number two. Still, we don't know label. We'll just say cluster one, cluster two without labeling. And if they have fins, fins are specific to creatures that are underwater, so they are in cluster three. So this is how unsupervised machine learning is trying to describe the data. Unsupervised machine learning is about description of the data, description based on certain features or the features that we extract from the data set. Or if we are given features, we will try to find patterns in the feature and it will just divide the data set, it will make clusters, right? So this is unsupervised learning. Again, unsupervised learning is about data description as opposed to approximation. Approximation, when I say approximation, approximation is a function that maps inputs to output in supervised machine learning. So this is function approximation because we are not 100% sure whether this is right function or not, but this is function approximation, right? So in unsupervised learning, we are given this kind of a data. You can see all the crosses are red. There is no labeling. On the x-axis and y-axis, there are two features. They can be called x1 or x2, simple in simple term. But for the sake of understanding, I have written BMI. BMI is body mass index, and on the y-axis is height. And these are two features given in the data set, and we just plot it. We don't know any label. This is the total data set. If let's say given to a data scientist machine learning, then they can apply unsupervised machine learning to find patterns in the data. So training examples only has data set without only has data without correct labels. So data is unlabeled, right? And this is probably the output of clustering algorithm. So if you see from the naked eye, we can see that there are probably two clusters. They are like two distinct clusters in the data set. But if someone can say that probably there are maybe three data sets or three clusters, not data set, clusters in the data set. But this is what K-means or the basic idea of clustering, to find pattern and find clusters or the data points that are together that are similar. We will see what I mean by similarity or similar, but this is what unsupervised learning intuition is. So we are given unlabeled data or examples in the data set. and we'll try to derive structure from the data by exploring relationship between input examples. Like before, there is some kind of relationship or structure between the data points. So we can say that data points which are together are grouped together, or the data points which are similar are grouped together to make cluster. So this is what unsupervised learning would try to do, derive structure from the data set based on the relationship between input examples or input data, like this one, right? So unsupervised learning is about description or describing the data, right? We try to describe data based on the structure present in the data set. So this is like a whole complete intuition of unsupervised learning. If it was supervised learning, we would have labels written with each image. But now we are given unlabeled data. Let's say this is the data set we are given. There are images of certain animals. We can say that they are dogs or cats, but data set doesn't say anything. These are just images. So what would be the cycle of unsupervised learning? It will extract features if features are not given. In this case, they are only images. So we'll extract distinguishing features or distinct features, and then we'll apply machine learning algorithm. This is unsupervised because we don't have labels over here. So this would be unsupervised machine learning algorithm. And unsupervised machine learning algorithm, the output would be distinct clusters based on structure within the data, structure present within the data, right? So this is complete intuition of unsupervised learning. Now the question is how we can test this cluster. Where is the test phase? Like when we were doing supervised learning, so this was the complete training phase, and then we will supply an image and try out what we have learned, whether this is correct or not. This is in case of supervised learning. But in unsupervised learning, how we can test it? Still we can test it. We can have similar, like purity of the clusters, how pure is the cluster. We will see that how we can find this purity of the cluster. Or if let's say we are given 1,000 images, we make a cluster of one cluster maybe of 400 images, second cluster of 600 images. But if we have one image given as a test image and we know the label, we can just try out the cluster and see whether this image goes to the right cluster or not. So testing is still there. This is not true. Some people say that there is no testing in unsupervised learning. This is not true. We'll still test cluster in different way, whether the cluster given as output by unsupervised machine learning is right or not. So this is like complete intuition of unsupervised machine learning. So clustering is one of the most common EDA, exploratory data analysis technique. Usually before start of any machine learning algorithm, we try to explore the structures within the data. That even helps in supervised machine learning as well. Like what kind of structure is there so we can find best algorithm based on the data set, based on the EDA analysis. So clustering is one kind of EDA that we can do even for supervised machine learning problem as well. So it is used to get an intuition about structure of the data. We have already discussed structure of the data and used to cluster data into meaningful and useful groups. Meaningful and useful group. Meaningful is subjective term and it is based on knowledge of the domain. Or if we know a priori how many clusters are there, or if we have mixed bag, like let's say if we have 1,000 unlabeled data and maybe 10 or 15 labeled data, so we can find meaning from the cluster. So clustering is not meaningless, it is meaningful. We'll try to find the right structure, meaningful structures within the data. And it's about finding homogeneous subgroups. Homogeneous is about similarity. The cluster data within the cluster should be homogeneous, should be same. So then this cluster become more meaningful. If this is not homogeneous, there is no point of making cluster because there is no homogeneity in the data, right? So types of clustering usually that are present in the architecture, in the literature. K-means clustering is partitional clustering type. We'll see what I mean by partitional. It's partitions data, but K-means clustering is partitional clustering, right? There is another very important type of clustering algorithm. They are called hierarchical clustering. and most important and most used is agglomerative hierarchical clustering. If time permits, I will try to briefly cover this topic as well, but our main focus would be K-means clustering because K-means clustering is one of the most widely used clustering algorithm. There are many optimizations then done over K-means clustering like K-means plus plus or fuzzy means, but K-means clustering is one of the most widely used and one of the most basic clustering algorithm. And so we'll cover that. And then there is another class of clustering which is called fuzzy clustering. So now having a brief intuition, a brief idea of unsupervised learning, we'll see where we can apply unsupervised machine learning or where what are application areas of unsupervised machine learning algorithm. So first and foremost, it is used in market segmentation, maybe for advertising, for different advertising agencies use this. Let's say you want to divide customers or population based on their income. And if you have the right clusters, then marketing agencies can post different kinds of advertisement to different clusters of people, right? So if someone is earning too much, probably they can have advertisement of very expensive cars, right? Just an example, I'm just thinking and making this example, but there are many other applications of market segmentation as well. Let's say if you have right data of population age and weight, then you can segment them, and based on this cluster on segmentation, we can devise right kind of or right size of t-shirts or clothing based on this data. So market segmentation is very important application for clustering. And when you will think, you will have many different ideas of market segmentation example. Then another very important and very useful area of unsupervised learning is social network analysis. Social networking, I hope you all understand social networking is like Facebook, Twitter, that we are using every day, LinkedIn, and based on different kind of people talking together or maybe posting or commenting together, these companies can make clusters of people to understand which people are connected to what kind of people. So, and then we can make a cluster. And maybe we can do the same thing based on emails. Like certain group of people always send emails to and let's say X people or X group of companies or how many companies work together. So then this is like very useful information just from the data. We don't have labeled data. Just by looking at the data without labels, this clustering can give us so much insight of the data that is very useful for different application areas, right? So this social network analysis are again very important application area for unsupervised learning. Image segmentation and image compression, very important area again. This doesn't seem trivial or straightforward initially, but I will explain. It's so easy and so trivial. So let's say if this is an image of a parrot, and this image is coded with 10 million colors, let's say, or 24 million or 16 million. Let's say if it is RGB color and each channel is 8 bits, so 2 raised to power 24, so it becomes 16 million colors. But you can see that this parrot probably has at max 100 colors, maybe 150 colors. So then we can just have this data and we can make clusters of colors which is present in the data, and we throw away all the colors or all the coding information in the original image, and we code the same data or the same image with the clusters of colors. So let's say this is image with 8 colors only. For compression, this is very important, like unsupervised learning. This is only with 10. I have another example. Let me show you over here if I can find. Yeah, this is my image. This is original image coded as 2 raised to power 24 colors. So it becomes 16 million colors, right? Again, I have coded this image only with 10 colors. K equal to 10 means 10 clusters, only 10 colors looks okay. K equal to 20, bit better than 10. But look at K equal to 80. This is almost visually they are similar. I'm not talking about mathematically. Mathematically, they would be very different. But when we talk about compression usually end user is human, and human visual system is not sensitive to many small details, and this is exploited by clustering. So instead of 16 million color, I can code this image with 80 color or 100 color, and visually they are same. So we can very aggressively code this image from 16 million colors to only 100 colors using unsupervised or clustering idea or unsupervised learning, right? So this is very important application area again if you are working into compression or image compression domain, right? So this was the third application area, and the fourth one is organizing computer clusters in data centers. So in data centers, usually certain group of computers start working together based on the data they have or based on the job they are doing. So if we have this kind of analysis, then we can organize these data centers better, right? Again, very important area. And one of the most fascinating areas, astronomical data analysis. So astronomers are using clustering algorithms to analyze formation of galaxies, because this is like clusters of stars grouped together. So they make galaxies. So clustering algorithm is used in astronomical data analysis as well. So these, and one more, data or document clustering. So given the document, we can cluster them using different techniques. Let's say if we are given 1,000 documents and we extract some kind of information from those documents and start clustering them, we will see that maybe 500 of the documents are related to sports, 200 are regarding fashion, 100 is blogs or technology related blogs or document. Just by extracting right kind of features from the document and using clustering, we can find structure in those 1,000 documents, and we can just store them in the right archives. Or it is used in search engine as well, because we know that this document contains this or belongs to this cluster, and if user is searching for very specific term, so we find that term specific cluster and we can just retrieve those results. So again, very intriguing application area of unsupervised learning. Welcome back. In this video, we will specifically see how K-means clustering algorithm works. Just as a reminder, K-means algorithm is by far the most popular and widely used clustering algorithm, as I have said earlier in my previous video. So K-means clustering algorithm is an iterative algorithm, and it tries to partition data into K predefined distinct non-overlapping clusters. So K is hyperparameter, or K is number of clusters that we have to provide to K-means algorithm in order to run. So this is one of the thing that machine learning engineer has to decide. Sometimes a priori we already know what kind of or how many clusters are available in the data set, but sometimes this is not obvious. So there are certain techniques through which we can find right number of k or number of clusters. But if data set in such a way that from domain knowledge we already know how many clusters are there in the data, then we will provide exactly that to k-means clustering algorithm. And each data point in a data set is assigned to one of the clusters. So k-means clustering algorithm is an iterative algorithm first. Second, it partitions data into k predefined clusters, and each and every point would be assigned to one of the clusters. It is not possible that there are some data points that are not assigned to any cluster. So all the points needs to be assigned, or k-means clustering algorithm will assign each and every point to one of the cluster. So let's say if we are given this kind of data, right now we don't have any labels. So data is, you can see all the data points are in black. So we don't have any labels. And this is X1 and X2, two features present in the data set. And let's say we already know that there are three clusters. Our number of clusters is three, or k equal to 3. And we want to run k-means clustering algorithm to find those clusters. So let's see how it does. So initially I will show pictorial representation because visually it is very easier to understand, intuitive to understand k-means clustering algorithm, and then we'll see how algorithm would work for k-means clustering algorithm. So first step would be to initialize or randomly initialize 3 points, because we already know that number of clusters are 3, and these 3 points corresponds to cluster centroids or cluster mean. Right, so we have initialized these 3 points. I have shown them as three different colored stars. So we have cluster centroid in green, in cyan, and in blue. So this is like the first step. We randomly initialize 3 points as cluster centroid. So K-means algorithm, as I have already told, is an iterative algorithm, and it has two steps. So after initialization of cluster centroid, it has two steps. First step is cluster assignment step. I will explain what is cluster assignment step, and second is move or update centroid step. So we'll see step by step. So first, cluster assignment step. So in this step, algorithm will iterate over all the data points. So let's say we have from x1 till xm. So we have m points. So it will iterate over all the points in the data set. It will iterate on m data points, and depending on the distance to each cluster centroid. So we have already randomly initialized centroids or cluster centroid. So based on the distance of each point to the cluster, three different cluster centroid, it will assign each and every data point to the closest cluster or closest cluster centroid. So now you can see the data points based on their distance are colored according to cluster centroid color. So the data points which are nearer, and we will have I will explain notion of distance, but let's say this is Euclidean distance. So we'll find Euclidean distance of each point to the centroids of clusters. So if the algorithm is over here, it will find distance to this centroid, it will find distance to this centroid, and it will find distance to this centroid, and it will find the minimum distance. So in this case, this point is closest to green centroid or green cluster. So this point is assigned to green cluster centroid. So this is cluster assignment step. And what I have explained, algorithm will iterate over all the point, and it will do the same. It will find minimum distance to cluster centroid and assign to that. So this is first step. This is called cluster assignment step. Second step is move centroid. So it will calculate average of data points assigned to specific cluster and assign that value to cluster centroid. Remember, we have initialized randomly this centroid. So probably this blue point was over here. And after first step, these three data points were assigned to this cluster centroid. So move centroid step will make, or it will calculate average of all the data points that are assigned to that cluster, and based on that average it will move centroid to that point or to that value, right? So first step is cluster assignment, in which data points are assigned to cluster. Number two is move centroid. So it will move centroid, will calculate average of the data points present in the cluster, and that average value would be new cluster centroid, right? So these are two basic steps of K-means clustering algorithm. So after two iterations, this is how this algorithm has emerged. So up till here, it was first iteration, and here second iteration includes cluster assignment and move centroid step. And now algorithm has converged because for third iteration, nothing has changed. So if cluster centroids are not moving, it means algorithm has converged. an algorithm will stop, and K-means algorithm has find this kind of cluster, these three clusters for the given data set, which seems quite trivial, which seems okay that it has find right clusters, right? So conversion means if you keep iterating, nothing will change. So it means convergence has arrived. Right? So it just came in algorithm in algorithm form. So we are given input. We know k number of clusters. So this is hyperparameter to an algorithm number of clusters. It's a parameter or hyperparameter. And we are given unlabeled data set. So this is the data set we are given. We don't have labels. We don't have yi or y1, y2 corresponding to x1 or x2. We have only unlabeled data set. And xi or x belongs to n dimensions. So n is the number of dimensions in the feature vector. And we have m data points. So m data points of n dimensions. This is what we are given, right? And this is complete K-means clustering algorithm. So this is the input that is given to K-means clustering algorithm. We randomly initialize K cluster centroid. We will have a discussion on this randomness as well, because randomness sometimes gives local minima to the solution, which is not okay. But from algorithmic point of view, we randomly initialize this k. K is hyperparameter to the clustering algorithm, or it's the number of clusters that we want to find from the data. So randomly initialize k clusters, and we denote this cluster as mu, right? So we have mu1, mu2 up till mu k. Capital K is number of clusters. Later we will use small k as well. I will explain when we will use. So these are cluster centroids. We randomly initialize those cluster centroid, and as the data points was n dimensions, these centroids are also n dimension. Right? This is trivial. So we will repeat until convergence. So this is complete algorithm from here to here, right? So these steps will be repeated until there is no change in cluster centroids. So this is convergence. And I will explain why some statements are written in blue and some statements are written in red. But first, I will explain those statements. So algorithm will iterate over all the data points. M is the number, or M is the data points in the data set. And it will assign Ci. Ci is again a variable, index of closest cluster centroid to Xi. Remember, we have cluster assignment step. So this blue is cluster assignment step. So Ci is the variable corresponding to data point Xi, and which shows that this data point is assigned to this cluster. So this is cluster assignment step, right? If Xi is assigned to cluster number 5, then this Ci would be 5, right? And in concrete term, if data point x2 is assigned to cluster 5, then this C2 would be 5. This is what cluster assignment step is, right? And this is based on nearness or the distance. And I will explain, because I have explained earlier as well, and I will explain again. And this red step is move centroid step. So now this is iteration over all the data points, and this small k. Now this is small k and this was big K. So big K is number of clusters. In our previous example, this was 3. K was equal to 3. So we will iterate over all the clusters, and this mu k is the cluster centroid. Right? We will get average mean of point assigned to cluster K. So if cluster K, if we have data, let's say if we have 100 points and cluster K equal to 1, let's say first cluster is assigned 60 points. So then this 60 points would be average. So we will average all those points which are assigned in those cluster. We will add and we will average them, and that will be assigned as a new cluster point, cluster centroid mu k, right? This is average of all the points that are assigned to that cluster. Just I will explain again. So the steps shown in blue is those corresponds to cluster assignment step of K-means clustering algorithm. These are those steps. And this step is computing distance. This is whole notion of distance or closeness of data point to cluster centroid, right? What we are doing here, over here, we have a data point. This step is iterating over all the data points. So let's say if this is the data point, it will find distance to all the clusters centroids. So if these three are data center cluster centroid, it will find this distance. Let's say if this is D1, it will find distance D2, it will find distance to the cluster 3, it will be D3. And this CI would be this assignment would be index of closest cluster. So closeness, if this is this distance smallest, it will be assigned to D1. So what it is doing, distance of data point from cluster centroid, and it will assign that cluster centroid that has minimum distance or that is closest. So it is minimizing over k, right? So ci would be assigned to cluster centroid that is closest, that has minimum distance, and this is sum of squared error, right? You can see this is square term, so this is sum of squared error. So it is Euclidean distance squared and assigned to one which is nearest. Right? So algorithm will iterate over all the data points, and depending on its distance to each cluster centroid, assign data point to closest cluster centroid. Find value of k that minimizes this distance. In other words, right? I believe this should be very clear to you now. Now the second step, which was shown in red in this algorithm, is move centroid step. Right? That step, these steps belongs to move centroid step of K-means clustering algorithm. And what it is doing, mu k would be the average and mean of point assigned to cluster k. So just as a concrete example, for example, data point x1, x5, x6, and x10 are assigned to cluster 2, right? So they have like C1 equal to 2. I have written over here. Okay, C1 equal to 2, C5 equal to 2, 6 equal to 2, right? So this was cluster assignment step, first step. And then second step would be mu of 2, because they are assigned to cluster number 2, would be average of all the data points that are assigned to this cluster. So average 1 over 4, x1 plus x5 plus x6 plus x10. So this is just vector addition and then divide by 4. So this will give new value of cluster centroid or centroid would move towards the data points another way. Okay. So what if cluster centroid has 0 data point assigned to it? Usually if this happens, then usually machine learning engineers remove that cluster. Then in output would be k minus 1 clusters. But if it is utmost important, or we already know that we have k clusters, or we are sure that there are k clusters, then we'll reinitialize that cluster centroid which is removed. So this is one of the way around if some cluster centroid has 0 points. But this is just a corner case. I think it is important to let you know, but this is just a corner case. But most our focus is first those two steps. So this is move centroid step, and first step was cluster assignment step. So in cluster assignment step, data points are assigned to cluster centroid or clusters, and second step is based on data points, based on their average, their centroid is changed or moved to the mean value of all the data points present in that cluster. Right? So these are two steps. An algorithm iterates over all the data points, all the cluster centroids, and it will keep on iterating, keep on doing till until convergence. Right? So this is in totality, this is K-means algorithm. Right? Just for the sake of completeness of discussion, we have already seen this distance, because we are calculating distance in first step. In cluster assignment step, we are finding distance of data point to cluster centroid, and we have different choices of distances. So we have whole family of Minkowski distance, and this is the general formula for Minkowski distance, but usually we use Euclidean distance where p equal to 2. Euclidean distance is sum of this distance in different dimensions squared and then whole over square root. So we use Euclidean distance, but if there is very specific application where Manhattan distance would be maybe better than using Euclidean distance, or maybe Mahalanobis distance if data is skewed like this, then probably Mahalanobis distance would be better. But usually we use Euclidean distance in while running K-means clustering algorithm. Welcome back. Up till now, we have done basic intuition of clustering, and then we have seen graphically how K-means clustering converge and how K-means clustering work. And then in the last video, I have discussed how algorithmically K-means clustering can be implemented. Now, the only piece of puzzle that is left to completely understand K-means clustering is its cost function. When I usually do cost function discussion with the students, the first question is why we need to understand cost function for K-means clustering algorithm. So for me, for students, it's so much easier to give this idea that if they understand cost function better, they can understand algorithm better. And if they know what is the cost function, they can debug K-means clustering algorithm well. So if you are implementing in real life scenario K-means clustering, and if results are not good enough, but you understand all the nuts and bolts of K-means clustering algorithm, then it's become so much easier to understand to debug K-means clustering algorithm. So that's why for me, understanding cost function or loss function is utmost important for any machine learning algorithm. So let's begin. So before writing cost function, I will introduce few variables, and then those variables will be used in cost function. So the first we have already seen is CI. This is cluster assignment set. During cluster assignment set, we use this variable CI, and CI is index of cluster to which example xi is currently assigned. So let's say if example number 5 is assigned to cluster 5, then C5 would be 5, right? Or if example number 5 is assigned to cluster number 2, then C5 would be 2. So this is simply this variable that tells which cluster to which cluster example is assigned. Second variable is we have already seen is mu of k, and this mu of small k. Keep in mind this is small k and this is large k. And large k is total number of clusters. Right? So mu of k is cluster centroid. Mu is mean or average, as we already know. And centroid is again average and mean. We have seen that in previous video. Right? So we have seen Ci mu k is cluster centroid. So it just gives values where a cluster centroid is currently placed in a feature space, right? The thing that I'm adding another variable is mu of Ci. This is kind of a composite variable mix of these two variables. And mu of Ci is cluster centroid of cluster to which example xi has been assigned. Let's say if we know that example 5 is assigned to cluster number 2, then C2 would be 5. We know that. But then mu of C2 would be mu of 2. So this actually tells cluster centroid to which example is assigned. This is index of cluster, and this is actual value of cluster centroid to which example is assigned. Again, I will explain again. For example, if let's say xi is assigned to cluster 5, then Ci would be 5, as I explained earlier, and mu of Ci would be mu of 5. So this tells that cluster to which example Xi is assigned and what is the cluster centroid of that cluster, right? So just try to absorb this three variables. Ci is index of cluster, mu of k is centroid, exact value of cluster centroid, and mu of Ci is cluster centroid to which example Xi is assigned. That is it. I hope this is clear, right? So now objective function of K-means clustering is we are trying to minimize this cost function. J is cost function of variable C's and mu's. We have C's, we have mu's. So this is a cost function of two variables C and mu. And what we are trying to minimize by changing these two variables is this thing. And this is the distance of any data point to its cluster centroid. This is cluster centroid to which Xi is assigned. One more time. We are trying to minimize distance. Next slide I will show in graphical form, so it will be much more easier, but just try to absorb this initially. What we are trying to do with this objective function is we are trying to minimize distance of any point to cluster centroid to which it is assigned. In other way, we are trying to move cluster centroid to the point as close as possible, right? So this is objective function, and this is objective function of two variable C's and mu's. C is the index to which point is assigned and mu is cluster centroid, right? And we are trying to minimize over all the data point. So this is average 1 over m. M is total number of data points in the data set given, right? I believe it's very intuitive, and it's kind of similar as we have seen in regression. In regression, we are using sum of squared error, so it's kind of sum of squared error. And in regression, we are also trying to fit a line which passes through all the points as close as possible. And here we are also trying to minimize this distance of cluster centroid to every point. So intuitively, they are same. So this is K-means algorithm optimization function, right? So cost function is trying to minimize distance between data point xi and associated cluster centroid mu of ci. So this is mu of ci, and this whole term is distance, right? You can see this is the distance term, this is the distance, and we are trying to minimize this distance by changing value of c and mu. This is total cost function of K-means clustering algorithm. In other words, cost function is finding parameter mu's and c's to minimize sum of square distance, like regression, between example and cluster centroid to which example is assigned. This function is sometimes called as distortion as well, distortion or distortion function. So sometime when you go and read in the literature, you will find this cost function written as distortion or distortion function of K-means algorithm. Now this is graphical intuition of this cost function. So let's say these are data points and they are assigned to cluster centroid of specific color. So there are three cluster centroid. First one is green, second one is blue, third one is cyan, and the points with the same color are assigned to these clusters, right? So this mu of Ci is cluster to which this point, which is Xi, is assigned, right? So you are getting, because this is blue and this is blue cluster centroid. So mu of Ci would be exactly this position. And we are trying to minimize this distance by changing position of cluster centroid. Remember when we run K-means clustering algorithm in cluster centroid update, we see that this star moves in different direction. It can go here, it can move over here. It just tries to find best position given the data set so that its distance to all the data points to which it is assigned is minimized. So this is cost function visually. Now algorithmically, I will explain how we are improving or how we are reducing or we are finding minimizing this cost function. So this is the same algorithm I have shown earlier of K-means clustering algorithm. And there are two parts over here, right? There are two main steps: cluster assignment step and move centroid step, right? So this is loop one. And loop one is cluster assignment step, as you already know. Actually, this step is minimizing this J distortion function or cost function with respect to CI. Remember, in this loop, only CIs are moving. So actually, in this loop, we are minimizing cost function by making this mu's constant or only changing values of the CIs. So in this step, actually, we are assigning data points to cluster centroid which are near. So we are not moving cluster centroid. So that variable remains same. Only variable that we are changing is cluster assignment or C's. And in loop 2, it's just inverse. In loop 2, which is move centroid step, we are minimizing this cost function with respect to mu's. Here, cluster centroids are moved while we keep C's constant. So actually these two loops, mathematically speaking, if we combine, they are minimizing this cost function or distortion function of K-means clustering. We can prove this mathematically, but intuitively we can also say that, and I have explained this intuitively, that this cost function is getting minimized by these two loops or by these two steps. So first step is cluster assignment step, second step is move centroid step. In this step, centroids remain same or mu values, these mu's are constant, right? So these are constant, and in this step we are varying this mu's and c's are constant. Values of c's are constant. So in combination, these two loops minimizes in totality this cost function of K-means clustering algorithm. So up till now we have discussed loops of K-means algorithm, but there is something missing, one or two small details that I want to discuss further in this lecture. The first step is random initialization. When I was doing initial video of K-means clustering, I said that we will discuss this random initialization step. And so this is the right time to discuss this thing. So remember, before having these two steps, two main loops, we have a step called random initialization of K cluster centroid. So K is total number of cluster. We randomly initialize these centroids. We don't have any mathematical function that gives best value where the centroids should be placed, but we randomly initialize, right? So this discussion on random initialization of centroid will cover discussion on local optima, because once we randomly initialize, there is probability that we initialize in such a way that our solution or clusters would be stuck in local minima. And I will explain now what I mean by local optima or local minima, not the global one. Right. So this is the data set. I have shown the same data set in my initial, I have shown this data set initial videos as well. But just keep in mind, usually K number of clusters are very, very less than total number of data points in the data set. It doesn't make any sense if we have almost same number of clusters as data points. So there is no point of running K-means clustering algorithm. So usually we are in this scenario where data points are much more than total number of clusters that we are trying to find in the data set. So there are two strategies to randomly initialize these centroids, right? These centroids are depicted as stars in this image. So these are cluster centroid, and we know here k equal to 3. That's why I've initialized at 3 random points. So we can find random coordinates of this cluster centroid, but what usually we do, we pick k training example randomly and we initialize exactly on top of those data points just to avoid local minima, but still we can start in local minima. But let's say we initialize, this is the data set given, and we initialize our cluster centroids in this location, right? In these three locations. And I will show what will be the solution if we initialize over here. So this is kind of a bad initialization, and we will be stuck at local optima. So this is like a good example to show what is bad solution, right? So after second iteration, if we initialize over at these three coordinates, our final solution would look like this. And you can see that this cluster with green star has no data points associated with it. So actually we end up getting k minus 1 clusters. We try to get k, but we get k minus 1 cluster because this cluster has no data point associated with it. And in this cluster homogeneity is not good because data points are spread all along this x-axis. And this cluster centroid only get 3 data points. So this is due to bad initialization, we are stuck at local optima. Instead of getting global solution, our cost function minimizes like this, and we get cluster in this shape, which is not optimal solution. We can see visually this is not optimal solution. So this scenario actually depicts that our solution is stuck at local minima instead of finding global or a global optimum solution. But now, just on the contrary, let's say if we initialize, this is the same data set, but now we have, by chance, let's say, we have got good initialization, right? And I will show now what kind of clusters we will receive. So after second iteration, we have converged at the solution, and we can say that visually, if we see this data, we can find that there are probably these three clusters. These three groups of data points are together. And this is what KMeans has also converged or also given this kind of solution. So now if we, because of good initialization, our clusters, we got, first of all, we got exactly k clusters instead of k minus 1 clusters, like in previous example. And cluster data points are grouped well together. They are coherent. The homogeneity is good in this solution. So we can say that this is global optimum solution. So if we initialize at right points, our solution would be optimum, right? So this is like one of the issue with K-means clustering algorithm, like how to initialize. So if you are using K-means clustering algorithm for any practical application, this thing should be in your mind that by doing random initialization, you can get stuck at local optima instead of getting global optimum solution, right? So K-means can converge on different solution based on initialization. Like in my previous example, I also showed that if we initialize cluster centroid at different locations, our solution would be different. But this, just to hammer this thing again in your mind, that K-means can stuck at local minima and K-means can converge on different solution based on initialization. You have to be very careful. So just another example, that random initialization, we can find different solution, right? So if we initialize this data set using these three locations for cluster centroid, we will get this kind of solution. Still, this is not optimal solution because it seems that these data points should go over here in this cluster centroid, but still it's okay. It's not bad. But if you initialize by chance or randomly initialize this same data set in these three locations, after second iteration, this would be the final solution. And look at this point. This point seems to be coherent with these data points. And this is the solution. So this is just visually just to show all of you that by random initialization at different coordinates, we will get different solution. and those solution can either be optimal solution or they can be local optima or something in between, right? So this thing should be in your mind when you use K-means clustering algorithm for practical applications. Just another visualization for intuition. So let's say now this is contrived example. Let's say this is the data set which is given to us or machine learning engineers, and we visually can see that there are exactly three clusters in this data set. But I will show what is the impact of random initialization on this data set. So let's say if we get good initialization, we will find global optimum solution, which is like this. There are no surprises over here. But cause of bad luck, if you do not initialize it correctly, solution can stuck at local minima. So our distortion function is actually not global minimum. So instead of getting the right three clusters, which were like this, three clusters, now we have got one big elongated clusters and two clusters squashed together, which are mixed together. So this is like a K-means clustering algorithm stuck at local minima. It can't do anything. And even if we have worst scenario, we can find one cluster centroid without any point associated to it. So instead of getting K cluster at the end, we get K minus 1 clusters. So again, situation is not good enough. So K-means clustering algorithm is stuck in this scenario as well in local optima. Now, what is the solution? We have discussed a lot that K-means clustering algorithm can stuck at local minima. Now the question arises how we can get out of this situation, how we can avoid this situation. So one of the solution which you find in literature is this one. So instead of running K-means clustering algorithm one time on a given data set, what usually machine learning engineers do, they run it for let's say 100 times, or it could be X time, it could be 1,000 times, it could be 50 times, right? So if they randomly initialize K-means clustering algorithm, they run it and they compute distortion function. So you keep on running, let's say you keep on running. So these are different epochs that you're running on the x-axis, on y, the value of j, and you find value of j that is best, right? And you just keep those settings. So you randomly initialize, you run K-means clustering algorithm, and let's say this is the value of j you find over here. You randomly initialize again, run K-means clustering algorithm, and maybe distortion gets more even to minimize. So this is not a good idea. Then you run it again. Maybe you will keep on running. You will find something like this. So you know that this point is the best point you have find. So you keep those settings. You keep those cluster centroids for the given data set just to make sure that you always find global optimum solution. So this is one of the idea that instead of running K-means clustering algorithm one time, you can run it n times and keep on finding or calculating value of j or distortion function and keep those settings which best minimizes this j. So this is one of the solution to avoid local optima or to have like better random initialization, right? So after running 100 times, pick clustering that achieve lowest j, right? So this is what I have explained earlier as well. One last thing that is left and that has to be discussed, this is very important, is hyperparameter of K. Like how to know a priori how many clusters are there in the data set. Sometimes from domain knowledge, machine learning engineers have the idea how many clusters are there in the data set, then it's easier, but sometimes this number of clusters are not known. We don't have a priori information. Then what machine learning engineers can do? So how to choose value of K, number of clusters. So this is big K, number of total cluster in the data set. So K can be chosen by visually inspecting the data to find this thing. So this is one of the most trivial answer, like plot the data and see what kind of structure is there. So, but sometimes this is impossible, and I will explain why sometimes this is not possible. So let's say if we are given this kind of a data set, right? And we want to run K-means clustering algorithm, but we don't know what is the value of K. So if I ask you, how many clusters do you see in the data set? Maybe some of you would say that there are two clusters in the data set, right? Which seems okay to me as well, that probably there are two distinct clusters. But if some of you are really critically, if you analyze this data, you'll find that this is one of the clusters, and this is second cluster, and then this is third cluster, right? So probably some of you say that k equal to 2. For some of machine learning engineers, k equal to 3 would be the right answer. But if you really critically see the data, you find 4 clusters. Now, once I have drawn, probably you see it better, that probably there are 4 clusters. So visually inspecting the data is not the answer, is not the solution to find exactly how many clusters are there in the data set. So the next question is how to do it, how to find it automatically, how many number of clusters are there in the data set, right? So one of the most used method in machine learning literature that you find is called elbow method. So you run K-means clustering algorithm by varying this K number of clusters. So this is big K, and you keep on recording distortion. This is J, value of J, right? And if you are lucky, if you find this kind of a curve, you can see that probably this value of J is the value of K is the best value for the given data set, right? So number of K can be chosen algorithmically by looking at this graph, by looking at this. And elbow, probably you get the intuition, this is like a arm and there are fingers over here, right? And this is elbow joint. So you try to find elbow joint to find the best value of K, right? After that, after this elbow joint or elbow point, there is no significant improvement for J, or we are not minimizing much this value of J. So probably this point is good enough for the given data set. So this is one of the solution to choose right number of Ks, right? But if you're not lucky, sometimes you have this kind of a curve, we don't find elbow over here, then this is the intuition of machine learning engineer where to find or where to stop. So if you have this kind of a curve, probably value of 4 also looks fine, 5 also look fine. So this is like a hit and try, you find the best value. So sometimes elbow method works and sometimes it doesn't, but this is one of the solution to find right number of clusters in a given data set, right? And sometimes domain knowledge. Sometimes it's just domain knowledge that will help to find or the application. Let's say you don't have idea in the data set, but you know that why you're applying K-means clustering algorithm or how many clusters would be required in the next step. So you run it accordingly, right? So there is domain knowledge is very important in finding right number of Ks. So I have like given you all the details of K-means clustering algorithm, starting from intuition, then algorithm, and in the last, I have given you idea of objective function of K-means clustering algorithm. And last 10 minutes, almost last 10 minutes, I'm discussing few practical problems associated with K-means clustering algorithm. I hope you like this set of videos and you are now better equipped to apply K-means clustering algorithm for practical applications. Thank you.